All right, it's iron 2 sulfate, and so we'd have to write out the formula. Iron 2 sulfate solution is aqueous. Okay, then what? 2 mils of silver nitrate. Okay, silver nitrate's the formula AgNO3. Are we mixing anything else in there? No, and so this is the reaction. Iron 2 sulfate plus silver nitrate. What does it yield? Well, when we look at this, it looks like it could yield silver sulfate and iron 2 nitrate. But silver sulfate is borderline, you know. In fact, the solubility of silver sulfate is kind of on the high side, and so likely it won't precipitate, but it might or might not precipitate. But anyway, you could form silver sulfate solid. Sulfates are mostly soluble, except for silver, lead, 2, mercury, calcium, strontium, barium. Right? But silver is one of these borderlines, so maybe we'll see it, maybe we won't. But this is not a metathesis experiment. What is this experiment? This is a redox experiment. And so what are we doing with a double replacement reaction in redox? Well, it might happen, right? But likely we should look for other reactions that might take place. And so here's metathesis. This is potential. As far as acid-base, you know, do you see any acid-base reaction happening here, Bronsted? No. We have a couple of bases. We don't have any Bronsted acids, so we'll just skip it, except for water. And so let's go on to redox. For redox, what do we do? Well, what we're going to do for all these reactions, we're going to use the chart method. So what's the first step in the chart method? The first step in the chart method. Write out the ions. Okay, so what do we got? Iron 2, sulfate, silver, nitrate, and one species that's not an ion, but you should write out is. It doesn't have to be the ions. I didn't call this write out the ions. I called it something else. What did I call it? Inventory. And so we want all the major species. There's one major species missing. What is it? Water. A lot of people forget that all the time, but if you get in the habit of doing it, sometimes it's easy to forget because you look at it and you go, oh, water is not going to react. You know, you can automatically tell after you've done a bunch of these. But not until you've done a bunch of these, you know, you should include all the species. And then we just consult the chart. You know, when I consult the chart, iron 2 is what we call an OA, an oxidizer, and an RA. It appears on both sides of the chart. Sulfate's missing something. Sulfate is an OA with H+, but we're missing it. Since we're missing H+, the, you know, strength of it as an oxidizer is going to go way down because we aren't going to form what? Well, we don't form something, and that means the strength goes way down on this. I think you can see the pattern. Silver, that just occurs on the oxidizing side. Nitrate, again, this is missing H+. Since it's missing H+, it's like if you try to make a cake and you're missing flour, should you just go ahead and do it anyway? It doesn't make any sense, right? And so if this is missing a key ingredient to make your product, then how are you going to make your product? And so both of these species here are OAs, but since they're missing, we aren't going to factor those in, at least in Chem 1A. In Chem 1B, we do things more quantitatively. In Chem 1B, we can see with a very low concentration of H+. H+ is present, right? H+ is present in water. Where does the H+ come from in water? Or hydronium. H+ and hydronium, same thing. Where does hydronium come from in water? It comes from collisions of water molecules. You know, there's a small fraction of water molecules that have quite high energy. And those high energy water molecules collide and create 10 to the minus 7 molar H+, but 10 to the minus 7 molar H+ or pH 7 water is just not enough. Not enough to form the quantities of water that need to be formed. That's the reason why we have the H+ in there, is to form a stable product. And so, you know, that being missing, we aren't going to factor those in. And then a water is an OA or an RA. And then we go down our list and see, you know, what's the strongest oxidizer? Well, we go down and we see that silver ions would be the strongest oxidizer on the chart. That's closest to what? It's closest to fluorine. And then we look for the strongest reducer. The strongest reducer on the chart will be iron 2. This is going to be closest to lithium. And so what we do is we just copy down the reactions off the chart. And so if iron 2 acts as a reducing agent, then it gives up electrons to form iron 3+ plus an electron. If silver ion acts as an oxidizer, it gains an electron to form silver metal. And then we add these two reactions, making sure the electrons produced are equal to the electrons consumed. So we get iron 2+ plus silver ions yields iron 3+ plus silver metal. Okay, after we do that, we take the strongest OA and the strongest RA present and combine them, making sure the electrons cancel. What do we do next? What we do next is we look for a driving force. As far as driving forces go, we label the RA, the OA, and then we go in the reverse direction. In the reverse direction, again, as I said earlier, the half reactions are the easiest place to identify. So that's an OA in the reverse. This is an RA in the reverse. And then we look at the chart, you know, which side is stronger. Well, looking at this, it turns out that silver ions are stronger OA than iron 3, and iron 2 is a stronger RA than silver metal. And so we have a driving force. We're going from stronger to weaker, and we're done here. And so this is what happens in this particular reaction. When you observe this reaction, it turns out this metathesis reaction is very fast. So initially you see a white piece of PPT form. But this white PPT slowly converts into a black PPT. The black PPT turns out to be tiny crystals of silver metal. When silver metal's in microcrystalline form, it doesn't look silver, it looks black. In fact, when all metals are in microcrystalline form, these tiny, tiny crystals, they appear black. You know, because usually metals will reflect all colors of light, well black substances kind of absorb, and so the visible light's being scattered away or absorbed. And so that, in that sense, the crystals appear black. As those crystals grow bigger and bigger, then we see the metallic silver form. And so this reaction is actually two competing reactions. It turns out the driving force for this one's stronger, and therefore the redox one dominates. We see this competition for reactions, or we also see sequential reactions happen, etc. in this. And so this is the redox chart method. You can solve all these redox problems using this exact same method. This exact same method is not difficult. You just have to try it a few times and work through the bugs, and then you'll get it. Everybody does, eventually. And so, any questions about this? All right, so that was number 4. Now go to number 3 and do that, you know, and then number 3 is a bit more complicated. Maybe I should do that one. What is number 3? Copper and bromine. The reason it's a bit more complicated is because after you do the initial reaction, there are more that you do. And so we start off with copper and bromine. Copper is a metal solid. Bromine, this one I'm going to write AQ. The reason I'm going to write AQ is because pure bromine, do you know what pure bromine is? Pure bromine is a liquid. And in the redox chart, they use pure liquid bromine. Well, if we use aqueous bromine, its concentration is going to be reduced. But we're going to use pretty concentrated solution of aqueous bromine, and the reactivity will just take it as the same as liquid bromine. Of course, it's going to be a little less active or reactive than liquid bromine, but it'll still react. All right, what's the first step in the redox method? Inventory. So what do we have? We have copper, bromine, and water. Just three things. Copper, what is it? Reducing agent only. Bromine, oxidizing agent only. Water is both. And so we pick the strongest oxidizer, bromine, the strongest reducer, copper. So the reaction is between copper and bromine. And so we look at the chart. Copper solid goes to copper 2 plus 2 electrons. Bromine, now the chart has bromine liquid. We're just going to use bromine AQ plus 2 electrons yields 2 bromides. The reason we're going to use it is because bromine liquid is just too reactive. It's kind of too dangerous for this lab. And so a little lower concentration is plenty reactive enough without being too hazardous. Then add them up. Well, these two have been very easy because the electrons have matched. But, you know, if you go back in your notes, you'll see a case where the electrons didn't match and how we took care of that. You go back and look. Copper 2 plus 2 bromides. So is there a driving force? Well, here's RA, OA. In the reverse, this is the OA, this is the RA. And then are we going? Yes, we're going from stronger. If we just look at the chart to weaker. And so there's a driving force. Copper metal is a stronger reducing agent than bromide. Bromine is a stronger oxidizer than copper 2 ions. So we have a driving force there, stronger to weaker. And this is the reaction here. Now what happens next in the procedure? You split the product solution. You see it? What does it say? Does it say anything, or are we done? Confirmation test? Yeah, it is. We do 2 confirmation tests. What are they?
For copper, we add 1 milliliter of 6-12-HB.
Yes, good.
And for
Bromide, actually.
we add soda nitrate.
Yeah. And so what we're going to do is we're going to do confirmation of the products, like taking advantage of their properties. We didn't confirm the products in the last reaction. In the last reaction, the product should have been, you know, the precipitate, either the white precipitate or the black precipitate, right? Visually, you could see it. But in this reaction, are you going to see it visually? Maybe, maybe not, you know. Bromine in water is orange. You know, we got copper metal, maybe some of the copper metal's eaten away. Copper 2AQ is a light blue solution, and bromide is colorless. So maybe we'll see it, maybe we won't. It's going to be hard to see. You know, did a reaction happen, or maybe nothing happened? You know? And so what we do is we do confirmatory tests. We split it up into 2 test tubes. And so half of it goes here, the other half goes here. One test tube, we test for the presence of copper 2. And so we have a copper 2 ion test. The copper 2 ion test is, we're going to use a reaction that's very well known. It's a Lewis acid base reaction. Depending on the concentration of copper 2 is going to be light blue to colorless. If it's pretty dilute, it's going to be colorless. You know, so light blue to colorless, because these concentrations aren't that high. And what we're going to do is we're going to take this copper 2 ion and then react it with ammonia in a Lewis acid-base reaction. The copper 2 is acting as a Lewis acid. Ammonia is going to act as a Lewis base. And what happens here is 4 ammonias will attack. This kind of reaction is very common in Chem 1B. And so if it looks really bizarre, wait until Chem 1B and you do tons of these. It'll be pretty easy when you're there. But, you know, this we haven't really talked about. What it forms is this ion here. And there's a good driving force for this, because this is a stable, what we call a stable complex here. And this is a dark or deep blue color. Deep blue. And it's aqueous. It's not a precipitate. And so what happens is the color of the solution goes from light blue solution to a deep blue solution. It should be clear. We should not see any precipitate. So let me emphasize that by saying clear, deep blue solution. A lot of people say it precipitates, but there's no precipitate there at all. It's just like you're dyeing the solution. And so this is how we detect the presence of copper 2. In fact, you might have done this in Chem 4. I don't know if you did the qualitative with copper 2 or not. No. You probably did this, though, with chloride. One of the tests for chloride is adding silver nitrate. Well, bromide and iodide does the same thing. It forms a slightly different color precipitate, but sometimes it's hard to tell. And so we do the bromide test here. This bromide test has potential interferences of chloride and iodide. And to do this properly, you have to get rid of those interferences of chloride and iodide, which isn't so easy. And so this bromide test, we know that there should be no chloride or iodide, right? And so we'll just say that, no chloride, iodide present. Because we know what we mix together in the test tube. Well, anyway, if we have bromide present, you know, in the test tube, then all we do is this. We add silver nitrate. Now, silver nitrate, you have to watch out, you know. Bromine, you have to watch out. I remember, you know, I was in an organic lab. And bromine's used as an oxidizer all the time. It's a pretty decent oxidizer. And one of the students spilled a drop of bromine on their thumb and started to panic because they thought, you know. But bromine, if you think about its oxidizing ability, you know, how strong is it? Well, a drop of aqueous bromine, it turned out he survived. But he was really worried. But, you know, people have inhaled chlorine. Chlorine is much more corrosive. It all depends on concentration. Chlorine is much nastier than both. But if we have bromide present, this is what kind of reaction? What kind of reaction is that? Off-white precipitate just means it has a yellow. It could have a yellow color to it. It's off-white. A slight yellow color to it. What kind of reaction is this? Use a process of elimination. Oftentimes when you can't figure something out, you can use a process of elimination to narrow it down. Is it a redox? Redox, we can easily tell if the oxidation states change. Did the oxidation states change? Yes or no? Oxidation states change? No. It's not a redox, so that leaves acid base or metathesis. Use the process of elimination. Acid base or metathesis. Metathesis. What's the definition of metathesis reactions? Anybody have the definition of metathesis down? Definition of metathesis is favorable ion combinations. We got two ions combining, that's favorable ion combination, that's a metathesis reaction. So, the metathesis is the answer. And so these are just confirmatory tests for that. These are in addition. And so that is our redox, but we also saw metathesis and we saw Lewis acid base reaction here occur. And so next, you're going to work on these. Since some people are just pretty much done with the experiment 17, and some people are still working on experiment 17, I'm going to delay the demo here. And so I want to get the people not to waste time here and start with the 18 reactions, and then we're going to stop, and then we'll do some, maybe, well, we'll see. You know, basically you don't want to fall too far behind, because pretty soon I'm just going to cut it, and then we'll do it. But you know, a full lab period for 15 reactions should be plenty of time, you know, last time. So try to get it done quickly now, and then start working on these 18. The 18s take more time than those 17s, okay?
Are we getting it again?
The exam? Oh, are you getting them checked again? Yes.
Okay.
You're getting them checked. It's the same thing, you know. I'll check it off once.
And then for the exam?
The exam I'm going to give back on Thursday. I was planning to give it back today, but I'm not. I'm going to give it back on Thursday.
And then,
Also, don't talk about the exam yet during class.
and then the
Uh-huh.
homework notebooks, you said the
Yeah, the stockroom. I just left them. They're in the lost and found in the stockroom. So if you don't have your homework notebook, you can grab it right there. Okay. Okay, any other questions? So bring up your 17s and 18s, and I'll check those off. Okay. 18s, you got to write down the ones we did here. You know, it's got to be complete. Even though I did it on the board, I want you to write it down because, you know, surprisingly, I do it on the board, like 17, and then people bring it up to me and they said, I just copied it down the way you had it, but they didn't copy it down the way I had it. You know, they omitted some stuff or they changed some stuff around. So even though I do it on the board, I want to check it because you'd be surprised at, you know, how frequently that people miscopy stuff, maybe. Okay.